Good afternoon, everyone. Thank you all very much for coming. My name is Denny Cherry. My email address is right there on the very, very, very large screen. If you want to contact me, at the end of the session, I keep forgetting to say this. I have business cards and laptop stickers down here on the table. Feel free to come grab some, and then preferably, also email me. I've got my two lovely assistants down here who are going to be asking any questions that come online, hopefully in English, not in Polish, because my Polish is non-existent. So actually, tell you a little bit about me real fast here, and then we'll get on back to the stuff you guys actually care about listening to. So like I said, I'm Denny Cherry. I'm the CEO and principal consultant for Denny Cherry and Associates Consulting, based out of San Diego, California. I've written somewhere around 8 books, mostly on SQL Server. I've written various articles for various magazines, including WinIT Pro, TechNet Magazine, MSDN Magazine, and some other ones that I can't remember anymore. I've been a Microsoft MVP for 16 years now, and I believe I find out if I'm going to be an MVP again on July 6th, I think. I'm also a Microsoft Certified Master for SQL Server. I've been a VMware vExpert for, I think, 7 years now, and I've also been an EMC elect. Now, if we can have the house lights turned up just a little bit for just a minute, this is going to be the interactive portion of the session. Who is running SQL Server? I'm going to step up here so I can actually see. Who is running SQL Server 2022 in production right now? No brave soul. One brave soul has raised his hand. Okay. We're going to go all the way back as far as we need to. Who's running SQL Server 2019? Almost everybody. Okay, that's what I want to see. SQL Server 2017. A few people. Hey, lights, awesome. That makes life easier. SQL Server 2016. Okay, about half the room. Okay. So before that was 2014. Okay, about a third of the room, 2012. Less people, okay. 2008 R2. A dozen or so. And 2 guys just hold their hands up because they know where this is going. 2008. Oh, they've already tapped out. 1 person. Well, 2 more in the back. Okay, 2005. The same suckers. Oh, and a couple of new ones. All right, so that was 2005. 2000, 1 poor guy in the back. 7, nobody? Okay, good. So I've done this at every conference I speak at. When I was at SQL Bits a couple years ago now in London, well, a couple years ago being in the before times, before COVID, we got all the way back to SQL Server 6.5, and some poor guy was still running it. Thank you, nice man who controls the house lights, who can turn them back down. So, the things I want to talk about today. I want to talk about the various kinds of indexes that are available in SQL Server. I want to talk about some misconceptions that people have about indexes and about how they work. I want to talk about some downsides that there are to indexing, because there are downsides, there are trade-offs that we have to make when we put indexes on systems. I want to talk about some advanced index tuning techniques that are available in SQL Server. And we've got Q&A at the very end. If you have questions throughout, feel free to stop me. It's going to require yelling because I can't see a whole lot of you other than like this poor gentleman in the front row here. So let's talk about the different kinds of indexes that are available in SQL Server. SQL Server has a bunch of different kinds of indexes. Indexes are how we make SQL Server go faster. Does anybody remember the turbo button on your computer? Okay, a bunch of us are old enough that we remember this. For those of you that didn't raise your hands, back in the day when we had really old computers, in like the 90s, there was this little button on the computer that would make the computer go faster and make your video games look really weird. So you would push this and the computer would literally speed up. It would help overclock the system. So this literally would make the computer faster. Indexes are the turbo button, and that's what it's called. They are the turbo button for computers, or for SQL Server, and for all databases, really. So we have several different kinds of indexes that I want to talk about. The primary ones being those top 2, the clustered index and the non-clustered index. I'm also going to touch on full text indexes, XML indexes, and column store indexes, because those are the most common ones that we're going to use in database applications within our SQL Server environments. So our clustered indexes, you only get one of per table. If you've ever worked on Oracle, God help you, you are used to the concept of having multiple clustered indexes. We don't have that in the SQL Server world. When you create a clustered index on a table, that table is actually converted into a clustered index table, and from what we call a heap, because that's what the table is before it has a clustered index on it. So that clustered index is actually the table. So it is the base table that we're dealing with at that point. When you create a clustered index, you can have up to 16 columns as the key columns in your clustered index. So those are the columns that make up the actual clustered index and that are going to most likely define the uniqueness on your table. Now, the fact that it can have 16 columns is not a recommendation. It is a limitation. And the recommendation is to only have one column as your primary key column, or as your key column rather, on a clustered index. And I'm going to talk about why you want to do that more on the next slide. If you have XML indexes on the table, you can only have 15 columns as your clustered index, but again, still, we only want one. By default, when you create a table and create a clustered index on that table, the clustered index will be the primary key on that table. So the primary key is what defines the uniqueness of the values or of the rows in the table. So again, by default, the primary key will be the clustering key or will be the clustered index. It does not have to be. They can be different, and there are plenty of use cases why they should be different. The first one I can think of, and really the most common one, is if you have a GUID as the primary key on your table. You don't necessarily want that GUID to also be the clustering key. So what you'll do is you'll put an identity column on that table, or a sequence column, either one, and you'll have the sequence column or the identity column be the clustered key, or the clustered index, and the GUID will be your primary key. That way you can still define the uniqueness based on that GUID, and that will help speed up the SQL Server and speed up the application. Because the clustered index is the base table, the clustered index has to be created on the same file group as the actual base table itself. If you create it on a different file group, SQL Server will very conveniently move all the data into that other file group for you. So a friend of mine who lives in New Jersey in the States was working with a client a few years ago, or got a call from a client, and they said, hey, we've trying to figure out why our clustered index file group is so huge and our table file group is so small, because they had a file group for tables, and they had a file group for clustered indexes, and they had a file group for non-clustered indexes. And he said, okay, this is going to be the easiest consulting job I've ever had. That's because when you create the clustered index and you tell it on file group and it's a different file group than the table, it's going to move the data to that new file group. So please give me your $300 per hour that you pay me, and I'm going to go away after 1 hour. So clustered indexes should be as narrow as possible. This goes along with that one way up there where you want to have a single clustered or a single column per clustered index. And again, we're going to talk about this more on the next slide, so just keep that in mind. Now, clustered indexes are not required. There are people out there that think that they are required, and they are not. Any table does not have to have a clustered index, does not have to have a primary key either. Highly recommended that they do. Most OLTP systems, so most online transactional systems, you're going to want clustered indexes on all the tables. You're going to want primary keys on those tables as well. There are plenty of cases where you don't, though. Things like data warehouses, they typically do not have clustered indexes, because as they're loading in new data every day into the data warehouse, they don't want to have to resort the data. One of the things about all indexes is that when you put data into an index, or in this case into a table, the data is going in the order that you've defined for that index. So if you built your clustered index on the date column, then as the data gets loaded in, it's going to get sorted and inserted wherever the correct values go. So if the date that you're inserting is simply an ascending date, things are just going to the bottom, that's fine. If things are going to be using older dates, then they're going to be going in the middle of the index, and then SQL Server is going to be doing some weird things, especially in a data warehouse where you're loading in huge numbers of records all at the same time. So the other kind of index that you're going to spend most of your time working with when working with SQL Server databases are non-clustered indexes. So non-clustered indexes, you can have a lot of them per table. In all versions of SQL Server over 2008, you can have 999 non-clustered indexes per table. Now, unlike the previous slide, this is actually a recommendation. Put as many indexes on a table as you need to satisfy the queries that you're going to be running on that table. So if you have 30 different kinds of queries that you're running against a single table, then you're probably going to want 25 or 30 non-clustered indexes, because almost every query is going to need its own non-clustered index. The exception to that being if the queries that you're running simply have a subset of the columns of a different query, then they can both be satisfied by the same index. Older versions of SQL Server, so for you, like few folks that were running older versions of SQL Server, SQL Server 2005 and below only supported 255 indexes, or non-clustered indexes per table. The reason this was increased was because of things like data warehouses that actually do need lots and lots of non-clustered indexes, because the business is going to be running lots and lots of different kind of queries. And so 255 actually ended up not being enough. So Microsoft had to bump it up. So non-clustered indexes, just like the clustered index, can have up to 16 columns as key columns in their index. Now, unlike the clustered index, this is a recommendation. You want as many columns as you need to satisfy your query as key columns in your index. So if this means you need seven different columns in your where clause, you're going to have 7 columns as your key columns in your non-clustered index as well. So we can have as many as we need, up to 16. Non-clustered, or non-index columns rather, can be put in the index with what we call the include statement. So this is 2005 up. So it's been available as a feature for quite a while now. What include columns do is they're not sorted, so you can't search based on them, but what you can do is return them. So the easy way to think about this, anything that's in your where clause is going to be a key column. Anything that's in your select statement that's not in your where clause, that's going to be an include column. That way we can give it back to SQL Server, or we can bring it back to the interface or back to the application. And relatively easy and relatively painlessly for the SQL Server. And I'll explain why in a little bit. So SQL Server has non-clustered indexes, and they all contain the clustered index columns inside the non-clustered index. This is why we want that clustering index key to be as narrow as possible, because we're going to be duplicating that data a lot. So say we've got a table, and our clustered index is built on a big int data type, so 8 bytes. And say we've got 30 non-clustered indexes on that table. Well, we're duplicating that 8-byte primary key value on every single non-clustered index we have. So 8 times 30, that's 240 bytes that we're spending just storing duplicate copies of our clustering key. So if we've got a really wide clustering key, say it's a data warehouse and our clustering key involves a date and a product ID and a sales order number and an ID value, and it's like 30 bytes wide. Well, now if we've got 30 indexes on that table and that's a 30-byte wide key, that's suddenly 300 bytes of data that we're going to be storing on the hard drive. And not to mention, because we're storing that 30 bytes on every single row, we're not putting a whole lot of rows per page in our database or in our non-clustered indexes at that point. So things are going to get rather poor performance from a hard drive perspective, and we're not going to be able to store as many pages up in memory because we're going to be wasting all the space. So if you've got a table that is a heap, whereas you don't have a clustered index on it, we still need to have this relationship between the non-clustered index and the heap. That's why the clustered index is stored in the non-clustered indexes to begin with. But if we don't have a clustered index, we don't have a clustered index key. So SQL Server creates its own value that it's going to be able to store. And what we could do is call that a RID, a row ID. That RID is made up of 3 different values. Those 3 values are the file number, the page number, and the row within the page. And those are what the 3 things that make up the RID, and so that's what's going to be stored on all these non-clustered indexes. Now those values sound quite large, but it's actually only 8 bytes of data. So it's actually a relatively small amount of data. So we don't do this typically too much anymore. Back in the olden days, when I started working in IT, we had really slow hard drives because we didn't have flash, we didn't have NVMe, and our hard drives were basically 10,000 or 15,000 RPM hard drives. So what we would do to get the most performance out of the system possible, we would take the non-clustered indexes and we would create them on various file groups within the database. And those file groups have files on them that are all are all sitting on different hard drives and different physical disks in the array. So we would do this to get the most speed out of the system possible by isolating things out to their own physical disks. We can also cut down the number of rows per index, and I do this a lot, and it really helps performance quite a bit. What this is called? This is called filtered indexing. So before filtered indexes were added to SQL Server, we used to say that every row in the database was in every single index, and that's true unless you're adding a filter. What the filters let you do is literally remove rows out of an index so that you don't need to have them in there. So if you're never going to be using them, there's no point in having them in the index. So you can simply remove them from the index, make the indexes smaller, make the SQL Server queries faster. So one of my clients actually did this with amazing success. So they are a medical billing company because we have really crappy healthcare in America, and it's really stupidly run, but that's a whole different conversation. So what they do is every time you go to the doctor, you check in and you get a tablet, like an iPad basically, and you fill out your address and your insurance information and all that good stuff and hit submit. Well, their application only cares mostly about your current address, but it keeps history of all the old answers to all of the questions that they ask you. Well, the table that contains all these answers is something like 4 or 5 billion rows. It's rather large. So the queries were not performing very well and was taking a good second or two to get back the information that we needed, just because it is a very large table. So to make things easier on the system, we added an active flag to that column that simply said anything that's the current record, we're going to set as an active flag of 1. Anything that's an old record, we're going to set as an active flag of 0. So it's just a little bit field. We then built our indexes, and we built all our indexes for the system saying where the active flag was equal to 1, because 99% of their queries are all based on your current answers only, and they don't care about the older answers. So once we did that, the indexes were able to shrink down to about 600 million rows, and our queries became significantly faster. We were able to store significantly more data in buffer pool because we didn't need to go through it anywhere near as much data, and we had only the data we needed. I actually just used this 2 weeks ago with the clients as well, doing kind of the exact same thing. I built my filtered indexes to support the replication filtering that they had in place. And without the filtered index, every time a record was inserted or updated in the system, it took something like 3 or 4 seconds for the system to figure out if the data satisfied the filter. Once I added this filtered index, suddenly it became a 1 millisecond lookup. And so every time they added a record, it only added an extra 1 millisecond of processing time. They were quite happy with this change. So there is a difference between how unique and non-unique values are going to be handled in indexes. So when you create a non-clustered index, you have the option of saying that it's going to be unique or non-unique. If it's going to be a unique index, every value in the index has to be unique. That's, makes sense. If it's a non-unique index, then we need to add in a column because SQL Server in its indexes don't understand duplicate data. So I've got an example here up on the slide where it's employee IDs that have been entered into some sort of historical table. And we built an index based on the employee ID column. And because we're allowing multiple records for each employee ID, when we created the index as a non-unique index. And that's the default, by the way. So when we add this index onto the table, SQL Server adds in what is called a unifier value, or unifier column rather, into the index automatically. It's a hidden column. You can't actually see it, but trust me, it is sitting out there. So every time SQL Server finds duplicate data in the index, it's going to go ahead and add in records or add in values for that unifier column. And those values are going to be just 0, 1, 2, 3, 4, 5, and they're going to be duplicated for each different primary value. So here we've got employee ID 4, it's going to show a 0 and a 1. If we go down to employee ID 7, it's going to show a 0 and a 1 as well. Now, this unifier column is an integer data type. It's not a magic data type. We can't just shove whatever number we want into it. It is an integer data type, which means it has to follow all the rules of the integer data type. The important one being, it can only hold 2.14 billion values. Fun fact, you can overflow that. It doesn't happen often, but it does happen. So if you put in 2.14 and change billion rows of employee ID 4, eventually you will run out of unifier IDs. And SQL Server will throw an error message to you when you're trying to insert into that table. Trivia knowledge for you. The error message that it throws is error number 666, which I'm guessing they picked rather specifically because they didn't expect anybody to ever hit it. I've seen people hit it twice in 23 years or 25 years of doing this. So it does happen, but it happens very, very rarely. What is what? Oh, how can you fix it? The way to fix it is to delete rows out of your table. Or you can add another column into your index that it defines uniqueness and then make it a unique index. And if you have that problem, feel free to call me. I'd love to be the consultant for your company because you clearly have lots of records and lots of money. So the big difference between full text indexing and clustered and non-clustered indexes, other than how they're all made, is clustered and non-clustered indexes are going to be used automatically. I add them into the system, I create my non-clustered index, and SQL Server will simply use it automatically. Full text indexes, on the other hand, it does not use automatically. I have to tell SQL Server, hey, go look at the full text index. The reason for that is the language that I can use behind full text indexing is quite different than a regular select statement. So it requires the use of a predicate to make this work. And those predicates are going to look very familiar to any of the .NET programmers in the room, because these are going to be contains table, free text, and a free text table. So these are the same predicates you would see if you were hitting the Microsoft search service and calling out and having your .NET app go search stuff. And there's a reason for that, and that's because full text searching actually uses the Microsoft Search service under the hood to do some of its work. So the really cool thing about the full text indexes is that they don't index just text. You can have them index binary data as well. So Word docs, Excel docs, Adobe PDFs, anything you can read that has text values in it, you can index with the full text search. This becomes very powerful for when you're building applications, because you can build an application like, say, a human resources application for your company, where you load in the employees' resumes that they've sent into a var binary max data type. You then add that column as a full text search, and you can now search through their resumes with just normal Transact SQL. So you don't have to build an application that actually reads those files and parses them and stores them in tables and stuff like that. You can literally just take the resume and throw it into the document, or into the database rather, write a query that says, hey, search through all these records and look for SQL near server, as an example, and it will find all the resumes that have the words SQL near the word server. They don't have to be next to each other, but they have to be close to each other, and SQL will then bring them back to you. So you do all sorts of really powerful stuff with here. And it is a very natural language search when you're doing these full text search options. And that gives you a lot of power that you can then give to your users, because they can literally just fill in the text box in the application saying, I want to find this word near this other word, near this third word, and it'll find back all the matching records within that application. If you have XML documents inside your database, you can filter, or you can index them rather, with full text search. But if you do that, it's only going to index the values within the XML document. It's not going to index the tags or where the value was in relation to what tag it was in. If you want that level of functionality, I've got good news for you. We can do that with XML indexes. That was supposed to be what's on the next slide, but it's not. So the way full text indexing works has changed over the years. So when Microsoft first built it, databases were rather small, and the way they built it made a whole lot of sense. Unfortunately, databases have gotten a whole lot bigger over time, and the old way of doing things did not work anymore. So they actually changed it in SQL Server 2008. So back in SQL Server 2005 and below, so this is for like the 8 of you that are using these really old ancient versions of SQL Server, full text search would actually create the full text index outside of the database. So fun fact, in SQL 2000, when you backed up the database, it did not back up the full text search database. So when you would restore the database and try to run a full text search, you'd simply get an error message back. When you tried to tell it to, hey, that's fine, just repopulate the index. Oh, I can't repopulate the index because there is no index, because all the folder structures for that index are not there. So it would just freak out and not know what to do. You'd actually have to drop the index and then recreate it and have it repopulate. So you have downtime while this is all happening. The big problem with the way this worked was the order of operations that Microsoft had running within the system. So it would search the entire index for whatever keywords you passed in, bring back all the rows that matched back to SQL Server, and then SQL Server would run the predicate search on those various rows. So say I'm searching my full text index for something innocuous, like the word test, and that brings me back 90% of the rows within my database. Now I've got, with that, just a regular SQL predicate as part of my where clause that filters down to like 3 rows. I'm going to go bring back the 90% of my rows from full text search back to SQL Server, and it's going to then parse through that and find just the 3 rows that I actually care about. So in SQL Server 2008 and up, we actually flipped the order that things were happening in. We also moved the full text catalog into the database. So it's backed up as part of the database and it's treated just like any other object in the database. Most importantly, when I restore my database, that full text catalog comes with it and I can continue to use it, which is kind of handy and kind of important. So all the word parsing that happens is all done through the Microsoft Search service. So as long as you've got the language that your users are using installed on the system, Microsoft Search Service can use that language, DLL, and it will actually then parse that value and send it off into full text search. Full text search now only searches a subset of the rows that we're looking for. So this is backwards of the processing that it used to do in SQL Server 2005. So when I run my query, and my query has my predicates that bring back just 30 rows, and it's got my full text search keyword of test that would bring back 90% of the rows. Now I do my predicate search first, get my 3 rows. SQL Server then passes that over to the full text engine and says, hey, do any of these 3 rows have this value that I'm looking for? Now, a question I've had in the past is how do I tell SQL Server to use the old process because the old thing makes more sense for my specific application? And the answer to that question is install SQL Server 2005. That's your only option. And God help you. So one of the things, if you are going to be using full text search, the developers of SQL Server have recommended that you use an identity field as the primary key on that table and include that identity key in the full text search index. I don't know why they say this improves things, but when the guys that wrote the code tell me to do something, I tend to try to do it because they're usually correct as they can look at the source code and see why they're telling me this. I unfortunately don't have that access. So XML indexes. This would be really cool if this had been the next slide from that earlier slide, but I forgot about the other ones. So with XML indexes, this allows us to index specific nodes and values within our XML documents that are stored within our table. So if we've got our XML document in the table and we want to search inside those XML documents to find the rows that match based on whatever XPath query we've passed in, we can do that with an XML index. You can have up to 249 XML indexes per table. I don't know why you would, but you can. I've only ever seen 2 on a single table. If you've got more than one column that has XML documents in it, sure, I can see the need for more XML indexes per table, but you probably need to rethink your table design as well. This is one of the few places you have to have a clustered index on the table. You absolutely have to have a clustered index or you will not be able to create the XML index. And the reason for that is on the next slide. It involves how the XML indexes are actually built on the back end, which we're going to talk about. So every XML index can have what we call a primary XML index, or sorry, every XML column can have what we call a primary XML index, and up to 3 secondary XML indexes. XML indexes can only contain a single column. So unlike your non-clustered indexes, your full text search indexes, or your clustered indexes, which can all contain multiple columns per index, here we can only have 1. And again, this will make a little bit more sense once we look at the next slide and we talk about how the actual back end of this thing works. Older versions of SQL Server will break your online index rebuilds if you have XML indexes on the tables. This has been fixed in newer versions of SQL Server, but older versions of SQL Server are still going to have this limitation. So XML indexes are not for XML variables. They're only for actual physical tables within your database. Now, the question might come up as to why we want to look at and have XML indexes on our database tables. And the reason is that if you've got XML data and you need to search through it, XML indexes are going to dramatically improve the performance of your application. So a friend of mine had XML data in her database she was working with, and she would try to search through it. And every time she would search through it, it was something like 7 minutes to run a query to search through the table, because the table was rather large, of a few hundred million records. Once you put XML indexes on there, it immediately went down to milliseconds. So when they make sense, they really, really make sense. So let's talk about the primary XML indexes that are inside the system. So, and what the back end of this actually looks like. So when you create an XML index on a table, what it's going to do is actually create a hidden node table. That hidden table is going to have a clustered index on it, and that hidden table is then effectively the primary XML index. These bullet points are coming up in the wrong order, but that's fine. We'll just do that. So when you create this hidden node table, when you create that primary XML index, that hidden node table is going to have the primary key for your database. That's why you have to have a clustered index. And it's going to have 12 additional columns within that node table. Those 12 columns are going to be everything SQL Server needs to shred the XML documents and shove them into the database. So that's going to hold all your data. So effectively, again, this is going to be the clustered index on that hidden node table. This is going to dramatically increase your storage requirements of your database. So when you create the primary XML index, assume that your storage is going to go up somewhere between 200 and 500%. So it's a massive amount of storage. The trade-off here is speed. We're trading storage for speed. Easy trade-off. Right now, these days, storage is super cheap compared to what it used to be. So increasing the space requirements for a database, not that big a deal at all. When we create our secondary XML indexes, those are effectively non-clustered indexes on that hidden node table. That's all they are. So we can't access that hidden node table directly, but we know that they're there because that's how this whole system works. So there are three kinds of secondary indexes that you can create on an XML column: the path index, the value index, or a property index. So the path index is the node ID, or the path within the XML document, and the value. The value is those options backwards, because remember, non-clustered indexes are stored in sort order. So a value index is going to be the value followed by the node ID. The third one is going to be the property index, which is going to be the clustering in table, the base table's clustered index, the node ID, and the path. Now, which of those should you be using when you're running your queries? That all depends on how you're writing your X query. I'm lazy, so what I like to do when I want to figure out which one of these I need to use for my application, I just create all three of them. I run my query. I then look at the execution plan for the query. It'll tell you which one it's using, and I delete the other two. I do all this in dev, so I look really smart when I go ahead and release it to Go in production. So it just works at that point, and the application just does things. Now, beyond those four different kinds of indexes, there's a new kind of indexing that's available in SQL Server, and you may have heard of it. People have been talking about it now for a few versions of SQL Server, and this is the column store index. The reason people have been talking about this so much is because this is a totally different way of doing indexing in SQL Server. It's our first B-tree-less index. So everything we've had up until today, think back to computer science class in college, has been a B-tree. So it's been a triangle, root page, intermediate pages, data pages down at the bottom. Clustered indexes do not have that, because they store data in a very, very different way of doing things. So think about a normal SQL Server table as an Excel sheet, just a giant Excel sheet with a billion records in it instead of a million. With the column store index, we simply change, we don't index the entire row, we break down things into individual columns and use those columns to store the information in our table. So everything in the first column is put in a separate set of database pages, and is then compressed down and made searchable by the column store index. Second column does the same thing, third column does the same thing. This makes it extremely fast to search through, because when we tell SQL Server, hey, select star from table where column A is equal to 5, it's extremely fast for it to do that because it's only pulling a very small subset of the table off the disk. With a normal B-tree index, when it would scan through that looking for that value, it would have to load the entire table and all columns off the disk to search through that, because that's the way the data is stored on the actual physical hard drive. With a column store index, though, we only have to load up just that one column. We find the records we're looking for, and then we simply can return them. And it's much, much faster and much more efficient for it to do it. SQL Server also has other ways to figure out if it actually needs to look at the data on that page as well. When these pages for column store index are written into the server and written onto the hard drive, the header of the database page will actually contain the range of values that are stored on that page. So when we go through looking for an ID number of 5, SQL Server will pull up the page, look at it, it'll look at the header, and go, hey, what range of values are stored on this database page? And if the page contains 5 within that range, it will look through that 8K page. If that page only stores values 10 through 50, we simply ignore that page and move on to the next one. So SQL Server can very, very quickly and very, very efficiently spin through all these things as fast as possible. So this is just a diagram of how it stores things. We'll ignore that. So use cases. When would you use column store index versus B-tree indexes versus traditional indexing? The big use case for column store indexes is where your data is going to continue to grow extremely large, and you have to keep performance exactly the same, and you're using large aggregations over that data. That's where you're going to get the best performance out of column store indexes. So when you're using large aggregates of data, so sum, average, min, max, those sorts of things, that's where column store indexes are really going to shine. If you're looking for a single row of data, column store indexes are not going to be what your application is going to be wanting, because it's not going to make the best use case out of the column store index. What you can do, however, is you can have a clustered column store table, and you can have traditional non-clustered indexes on top of that. So if you've got a situation where you've got reports that are being run by the business unit on the database table, and you've got a traditional OLTP transactional application on that table as well, you can have point lookups using your non-clustered indexes, and you can have the reports then using the column store index. You can have the best of both worlds. And Microsoft actually built that specifically for that situation, because while it's not what we want, it's what we're stuck with a lot of the time, because applications run reports off the database, and business units require those reports, and we need the whole thing to run awfully fast. So let's talk about some common misconceptions in indexes real fast here. The first one is that indexes do not require maintenance, and they actually do. We have a couple of different ways to do maintenance inside SQL Server. We have index rebuilds and index reorgs. As long as you're doing one of those, I don't care which one, then your database tables are going to perform much, much better, and your searches against the indexes are going to be much, much faster. So how do you know what you should be doing? Scans or rebuilds? You know, there's ways to look and figure this all out by looking at the fragmentation of the tables and seeing how fragmented things are, and if they're below 30% fragmentation, you use rebuilds, and if they're above 30%, you use reorgs. The much easier way than trying to figure all this out, writing the code and doing the research to figure out which one you should be doing, is to just simply download Ola Hanegren's maintenance code that he publishes on his website, ola.hanegren.com, and it's the gold standard of database maintenance. And you can simply download it. It's a SQL script, run it on your server, it creates a bunch of jobs, and you just schedule the appropriate jobs against your server to do the work on your box. And that will then help you maintain all this stuff, and you don't have to sit there and do any of the work. Most companies at this point are using Ola Hanegren's code to do their work. I know a lot of vendors that are redistributing his code from his maintenance jobs as part of their application to maintain the code within their application. Another common misconception is if I create one index for every column in my database, everything will simply be fine. This is unfortunately not true. The reason this is not true is because in most situations, SQL Server will use one index per table, per query, and that is it. There are very, very rare circumstances where you can get SQL Server to use more than one index in a table, but they are, again, very, very rare circumstances. The vast majority of the time, it's one index per table, per query, and that's it. So if all you've got is a bunch of indexes sitting out there, one per column, those are not going to help you. They're going to help a little bit, but they're not going to help as much as they could. Base table is sorted based on the order of the clustered index. This is sort of true if you're running SQL Server 6.5, because it actually stored the data in the same order as the clustered index. But SQL Server actually stopped doing this back in SQL Server 7. The reason for this is because we don't know where data is going to go, and we don't want to have to move huge amounts of data from one place to another on the actual hard drive. So now the data can be stored however it is wanted within the server. Within an 8K database page, the data will be in sort order. So if I've got a table and with an identity column of 1 through 10,000, rows 1 through 1,000 could be on page 700. Rows 1,001 through 2,000 could be on page 6. So SQL Server will put the data wherever it needs to within the database file. And again, the data within those pages is going to be sorted correctly. Another misconception: clustered indexes are required. Again, there are very few places where they are actually required. There are lots of places where it makes sense to not have a clustered index. Like I said, data warehouses make a lot of sense to not have clustered indexes because we don't want to worry about sorting the data as it comes in a clustered index, or in a data warehouse rather. So let's talk about some of the downsides to indexes, because we work in IT. Nothing is free. Everything has a cost. It's just, is that cost going to make the most sense for you? First downside: indexes take up space. Indexes take up a lot of space. I've had customers where they've come back to me and said, yeah, we know we need to create these indexes, but we can't because we don't have the space to store them. Specifically, one of my customers that I'm thinking of, they work in the medical field and they sell software. They're a vendor, so they sell their software out to hospitals and doctors, clinics, and stuff like that. And what their software does is it basically monitors the temperature of IV bags in IV machines and in refrigerators as they're being prepared to be used by the medical people. So they can't go to their customers and go, by the way, in this next release of our software, we're going to quadruple the amount of space that you're using. So just like FYI, you should plan for that. So it's just not something they can go to their customers. They're slowly adding in the indexes over time, but they've got to be very careful about how they do that because they don't want to go back to their customers and go, by the way, your terabyte database is now a 4 terabyte database. Sorry. Indexes slow down inserts, updates, and deletes. Yes, they do. Very, very small amounts. Every non-clustered index that you add will slow things down by about 1 millisecond. Your insert, update, deletes are going to slow down by a millisecond or half a millisecond. Because as you insert data into a table, it's going to be inserted into all the other indexes. All the indexes are on that table. However, we're okay with this because we're speeding up our select statements dramatically. One of my customers, when they added indexes onto a table, select statement went from hours to milliseconds, just by adding an index onto the table, because we were no longer scanning through the entire table. So the indexes are very much worth it, and it's worth having them on there. I talk to developers all the time, and they tell me, oh, we can't add the index because it's going to slow down the insert. Okay, how slow is the select statement? 3 minutes. Okay, you're okay with that, but you're not okay with adding a millisecond to your insert time. I think you've got your priorities backwards here, buddy. We care more about people using the application. I heard a metric years ago when I was reading an article. It says you have 2.5 seconds to do something in your application. If you spend more than 2.5 seconds waiting for the screen to pop or waiting for the command to finish, the user is thinking about something else. They're no longer thinking about the task in front of them, the task that they're doing. So that's a goal that I set for myself whenever I'm doing performance tuning. I don't want anything taking more than 2 seconds because I know the UI still has to do stuff. So I want to make things as fast as possible because I don't want to be the cause of the application taking more than 2.5 seconds to do something, because that's a really short amount of time. Using the wrong index can make your application slower than having no index on the table. So if we've got a table and we have the wrong index in place and we go to scan through the table, we're going to have to do a bunch of extra work. And that extra work can be found in the execution plan as what is called a key lookup. Key lookups, or bookmark lookups, depending on if you've got a heap or a clustered index in place, are going to be extremely slow for your SQL Server to process. And that's because of what they're actually doing. So when you've got the wrong index in place, you're missing columns in it. So SQL Server is scanning through the index, finding the rows that it needs, and then going, oh, hey, I'm missing this other column. So I'm going to go back to the base table and go get it. Now, the problem is that SQL Server does that for every single row it's returning. So if you're only returning one row, not that big a deal. It's a couple of extra I/O. It's adding 2 milliseconds. Who cares? The problem becomes when it's like a dashboard in the application, and that dashboard is returning back 10,000 rows. So now, for every single one of those 10,000 rows, I'm doing a lookup over to my clustered index to go get the rest of the columns that I need. That's like 3 or 4 I/O per record. So now suddenly I'm doing 30, 40, 50, 60,000 extra I/O. I/Os are time. Keep in mind, the slowest component in your server is the hard drive. If we're reading the hard drive, or from the hard drive, 30 or 40 or 50 or 60,000 times, that's actual time that we can measure with like a stopwatch. So it's going to take seconds to run every query as opposed to milliseconds, and we want milliseconds out of our systems. When you're building your application, if you've got encrypted data cannot be indexed very efficiently at all. And this is simply because of the way encrypted data is stored. The data is encrypted, so it's really hard to look it up and really hard to do where clauses against that. If you've used or looked at Always Encrypted in SQL Server 2019 or 2017 and above, you will see that you've only got a couple of different storage options, and you have to pick one. You can either tell Always Encrypted to store data so it can be searched, or store data so it cannot be searched. And basically the difference between those is what we call the salting value on the encryption that it does. So if it's the searchable kind of Always Encrypted data, we just take the value, encrypt it, and store it so that we can search against it. If it's a non-searchable value, we'll take the data, add on a salted value, or a salting command, or salting value, and then encrypt it and then store it. The reason we cannot search against that is because when we take the user input in, we don't know what salting value to use to encrypt it with. Because if we just encrypt it without a salt, and we search against a salted column, you're not going to get a match because the value is never going to be the same. So the way Microsoft got around this in Always Encrypted is by taking the searchable version, encrypting it without a salting value, and storing it. When the user passes in a value, we encrypt it with the same algorithm, so we get the same value back, or we get the same value, and we can actually do our matches at that point. This is why you can only do equality matches in Always Encrypted, because there's no way to do greater than or less than, because we're now dealing with not the actual value, we're dealing with the encrypted values instead. So let's take a look at a couple of advanced index tuning techniques that can make your indexes even faster. The first one is a thing called fill factor. So what fill factor does is it tells SQL Server how much space to leave on the database page when it's either creating or rebuilding or defragging the index. So what I mean by that is think about the way SQL Server stores its data. It's an 8K page. If that page is full and I try to insert a value that's in the middle of that page, there's nowhere to put it because the page is already full. So we actually have to take part of that data off, move it to a new page, and then we can insert our row. This is what we call a page split. They're expensive because we're doing 3 or 4 reads and writes instead of just one. With fill factor, what we do is we tell SQL Server, when you rebuild this index, rebuild it and leave 30% of the space free. So fill factor is 70, means I have 30% free space on the page. So that way, when I've got all this free space, I can take, I've got all my free space. When I go to do my insert, I've got enough room on the page to insert that record, and I don't have to do any of my page splitting, or at least not for the first part of the day. The goal when doing index rebuilds is to free up space on those database pages and get rid of a lot of this fragmentation. So we simply do that by doing that database maintenance. We also have this setting called padding. So padding tells SQL Server, take the fill factor and apply it to the navigation part of your index. So if you've got a naturally ascending key column, so something like an identity value or a date where you're only inserting values into the bottom of the table, you would want your fill factor set to 100, and you would want padding off. Because there's no point in having free space. You're never going to be writing data into the middle of the table. And if you are, it's a known situation, and you know to rebuild stuff after the fact. With padding, with a non-ascending key column, so something like an index on a name field, for example, names are not always in the same order. We don't get our customers in alphabetical order. It would be really nice if we did, but we don't. So we want to leave free space on those pages so that when we get our new customer whose name starts with C, my last name, for example, we can shove it in the middle of the database page and we won't have our page splits. Padding becomes very important because it's applying to that navigation part of the index, and page splitting that is extremely expensive. Because if we page split the navigation part and we have to split off one of those intermediate level pages, we need to write to every page underneath that. So all the data pages underneath it and any intermediate level pages that are also underneath it, of where this new page is and how to find the data that's on it. So it gets very, very expensive to split one of those navigation pages very fast. We have the online index rebuilds. These are going to be determined based on what version and what edition of Microsoft SQL Server you're running. Newer versions of SQL Server, basically anything 2016 Service Pack 1 and above. I know it's a weird cutoff point, but it is. Online index rebuilds are available in Standard and Enterprise Edition. They're actually available in Express as well. SQL Server 2016 below Service Pack 1, so SQL Server 2016 RTM and below, online index rebuilds are an Enterprise Edition feature only. So that's going to be something to keep in mind. What do I mean by an online operation versus an offline operation? Online operation, users can keep using the table or using the index while I'm doing index maintenance. With an offline operation, the users cannot continue to use the table during an online operation. Now, personally, I love this slide because this is the entire sample code of everything we've just been talking about. Creating a non-clustered index, very straightforward. Create index, whatever the name of the index is going to be, on whatever the name of the table is that you're working from, on whatever columns are going to be in your index. So think of an index like a select statement. So in this particular case, I'm doing select column 1, column 5, column 3 from my table. That's what's going to be happening when I create this index. The data is going to be sorted based on those. So actually it's going to be select column 1, column 5, column 3 from my table, order by column 1, column 5, column 3. So that's how the data is going to get shoved into the index, and that's how I'm going to be searching for it. When the order of my indexes, or the order of my columns rather, within the index depends very much on the selectivity of the data. You want to eliminate as many rows as possible, as fast as possible with your index. So you want these to be incredibly unique values by the time this comes back. So everything in your where clause is going to be one of those key columns up there at the top. Everything in your select statement that is not part of your where clause is going to be in your include. So there I've got include column 4 and column 2. So those are just coming along for the ride. That where clause there, that's my filtered index. That's my filtering. So here I'm going to be doing only the records where column 6 is equal to value 3 with my fill factor of, in this case, 70. I've got padding on. I'm doing an online rebuild, and I've got data compression that can either be row or page. So I can tell SQL Server, hey, compress this either by row or by page. If you have any questions, I'm perfectly happy to take them now. And unfortunately, we are all out of time, so we're just going to go ahead and go on right to the next slide. I will be up here if you have questions. Please feel free to come up and talk to me. Like I said, I've got stickers, I've got business cards. Feel free to come grab them. Thank you all very much for coming. Don't forget to go see the sponsors and thank them for coming, because they can't have great events like this without the people that actually pay for it. So thank you all very much for coming. Have a great rest of your day.